For me, wind is a really, really interesting topic. It's fantastic because there's so much about it that makes it an important part of our world. It's a natural energy resource, obviously. I love sailing. I love flying. I love everything about aerospace. And then the next question becomes, well, okay, if you like it so much, what do you know about it? So for the world of mechanical engineering, wind is a fluid. For the purposes of trying to understand how it works, you need to think about it as a fluid. So what I'm going to do is I'm going to share a couple of ideas with you right now so you can figure out how to evaluate our process. What we did is we came up with this project and how it led us down this path. So the first thing to know about wind is that wind is a fluid. All right, wind will move, it'll eddy, it'll move around you, it will separate long before it ever gets to you, and it will actually make power based on the turbulence that it is generated by. So what happens is you've got to figure out how to use that turbulence to your benefit. Wind is also going to make powers at different levels. Turbulence will happen a lot more at a lower level and will decrease as it gets higher, which helps wind speed. And wind speed is actually the key to wind power. And wind power is what we're talking about with this project. We're trying to figure out how do we mitigate the situation in an urban environment, this is where our project is, and increase wind speeds to the point that we can actually make a viable project out of it. Or can we? When we start looking at wind, we start looking at placement of turbines. These are vertical axis turbines. They work a little bit differently, and I'll talk about that in a little bit. But what you need to know is that you can't just sit here and say wind is going to come straight across this building and you're going to catch a 50-mile-an-hour breeze if it's 50 miles over here all the way across the building. There's all kinds of things that happen, and if you want to think about it, all you got to do is think about a rock in a stream and what's happening with that rock, what's happening behind it, in front of it, and that will start to explain how these things start to happen with wind itself. You can also look for anomalies. When you start thinking about sighting, when you start thinking about how wind works, you can look for areas where you can create an anomaly, possibly funnel wind in to increase wind speed. Wind speed, again, is wind power, and power is what's going to make the electricity, which is going to get you where you want to be. You can also look for natural situations or situations that have been created for you. This is a fantastic clip from the news earlier this year in Panama City. It shows how the wind shooting across the ocean here hit these buildings. And again, when you start thinking about placement of wind and wind power and wind turbines, if you thought you could make the same power right in the middle of the building as you could at the leading edge, you'd be completely wrong. And if you thought that you would feel 50-mile-an-hour winds coming straight across the top of the building, you'd be wrong, because actually what's happening is the wind comes up, it compresses, and it shoots straight up over the top. You couldn't get a better wind tunnel photograph than that. So the question is, how does a wind turbine work? Well, it's essentially a big motor attached to a blade that's going to spin because of the mechanical energy in the wind. It turns the rotor turns a great big set of coils in there, which passes around magnets, and the magnets generate electricity, and the electricity gets used by us. It's a pretty simple process. The hard part is trying to understand the scale and the relevance to you and me. So I don't know if you saw the little turbine on the buildings, but that's about this high. It's about 30 feet high. When you look at what the utility is using these days, it's about that big and bigger. Now the difference is the amount of collected area. So you're talking about wind power. You need to collect a certain amount of energy in the wind in order to generate a certain amount of power. There's a proportion for it. And part of the proportion is understanding also that there is an exponential relationship between speed and power. So not only is it to your benefit to catch more wind makes a lot more energy, but it's also your benefit to catch exponentially, to collect higher wind speeds. So you're going to constantly look for situations where you can hit a higher wind speed, because what happens is there's a great relationship between wind speed and power. If you double the wind speed, you can actually make 8 times more power. And that's a huge increase, which is why everybody biases towards areas where if you go from, say, 10-mile-an-hour winds to 20-mile-an-hour winds, you get 8 times more power. That's a huge boost in power. So people will try and create situations for that. One more piece of information for you. There's a couple different types of wind turbines. Everybody knows what these are. These are propeller turbines, basic technology. There's a lot of effort going into understanding twist and speed and length of the rotor. What's great about them is that they can actually catch flow as the wind changes direction. They can also change direction instantaneously, because there's constantly a blade going into it. The problem with the propeller turbines is if the wind shifts 10 or 20 degrees, they're going to lose efficiency dramatically. And then you're going to have to figure out how to get your head to shift with the wind quickly, or hope that the wind comes right back on center. So you're looking for consistency These are a couple different variations where we're hitting the edge of the marketplace right now. This is a two-bladed foil. This is a designer. I think he's wondering why it's not spinning. You know, these are actually notoriously not very good. The three-bladed ones are actually starting to come into vogue now. There's a really great mechanism that happens naturally by putting blades in a helix format, because now there's always a blade or a portion of a blade pointed into the wind, which means they're easy to start. This is actually a company that's testing out with Benrel right now, and they have a blade system that's called Blackhawk, and it's similar to helicopter linkages. And these blades can actually auto-trim themselves. We're looking at the edge of, right now, where we can be in wind energy. You have two different classes of wind. You guys know about big wind most of the time. Almost everybody knows about big wind. It's commercial scale. It's usually offshore, maybe in the Great Plains. Micro wind happens at a smaller scale, but the idea is to build micro wind farms that will collect enough energy to and be flexible enough in their placement that they can take advantage of these anomalies that happen in urban environments. And of course, you can start to see that you can start designing with them at this point. That gets us to the next level, which is the edge of wind design and integration into our built world. It's figuring out how to jump the problem that we have with electrical transmissions happening over long distances. We don't have an infrastructure right now that's built to handle wind turbine farms in the middle of the country for power situations out here. So this is a building that was built in China. It's called the Pearl River Tower. They put like 8 turbines in here. They spent some good time here developing the flow here so that as the wind blows at it, it funnels the air through these generators right here to power the building. It doesn't take up the entire building as far as power resource goes, because again, you're not talking about a huge amount of collected area, but you are talking about an incredible amount of speed. So this is Manhattan. This was a project that we were presented with. Took place up on the Upper West Side. You can see we're looking at the south end of the island. In New York, does have some fantastic avenues for wind. What happened is most of the wind comes out of the northwest, which aligns with the avenues here. And that wind has the potential of accelerating, coming through some of these buildings here and coming across our target building here. And so we were tasked with understanding what could we do in order to make this project viable. Could it be viable? Our resource is determined by this. This is a real basic tool. It's called the wind rose. And it tells us the frequency and direction of wind at any given site. We know that seasonally it changes, but for the most part we're working within this vector here. And that means that our wind is coming across the river and through the avenues, and Fort Washington neighborhood is up on a cliff. So that means we've got altitude working in our favor too. What we have working against us for solar, you can see the hospital right here. We also have this building here and a row of buildings over here. So we were wondering, what does this mean? How do we give our client a good understanding of whether or not this project is viable? Do we potentially have some anomalies here that are going to make this whole project come together and be something surprising? Or perhaps it's a no-go. And how do you tell this? So we started isolating the various constraints we had. We started identifying building 1 was a huge problem, or potentially there was some flow and something that happened here that made this whole thing work. We had 3 tall towers across here. Everything else is lower than the roof, so we're going to be dealing with the surface turbulence there. We said site A, which is at the top of the ridge, was going to be the best site, although it's the hardest to build on. Sites B and C were out there as well. And we started the evaluation process. We started looking at different ways of trying to figure out how to tackle this, and ultimately came down to the fact that we just needed to build a model of the entire area. So we took a 12-block area of the city and we modeled it. Measured all the buildings, we built a 3D model, and we put that into a set of software called CFD software. It's computational fluid dynamics. And we set up the sites. We took all the sites, which you can see right across here. Site A is up along the ridge. B here, C on the other side, D over here. And we inserted that into our model. And we did some flow analysis on this building. You can start to see where the turbulence happens and the flow happens. Here you have all the flow working between the buildings. You can see the acceleration right here. You can see the back-end turbulence across here. This is the direction of flow. You can see that there is some bubbling around here. So we quickly isolated this area here, which was their favorite, as a no-go site. It was pretty obvious. You can see some fantastic accelerations between this building. So what we did was we built a matrix. Once we did all of our slices, once we tried to decide from every possible wind direction and the dominant ideas, well, this was a complete no-go area. This area here worked. This area over here worked only from the west. This area here actually worked exceptionally well, and if you can remember, this area here worked well because of an acceleration through here, but the minute the wind shifted to the north, it was basically done. This takes us to the next step is, where's the project right now? The project hits the wall because of everything else that happens with the wind industry, which is policy. And that's when you have to be able to step out and say, all right, how do we get the project to move forward again? And this is where we're working on it now. Well, what else can we do? Can we make the project better? Can we reach out and reach farther? How much further can we go with this? And this is where you guys come in. These are the Miller brothers. They were high school students that a couple of years ago, they won the Intel Foundation Award and the Edison Award for a project they did. And what they did was they drew their inspiration from the foils on whales. And they created a series of nodes and nodules along here that actually increased the efficiency of a wind turbine blade.